The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, morning, whatever it might be, wherever you're at. Welcome to the Weeks 3-4 S2S webinar series. I'm Mark Olson from the Weather Program Office S2S program, and I know many of you are aware this webinar series is co-sponsored by the OAR Weather Program Office S2S program and the National Weather Service OSTI modeling program. And so before we begin, I wanted to remind everyone of the webinar series website, as I always do. The address is posted in the chat box there, and I'm showing it on the screen right now. But on the site, as I always say, you can find information on past talks. Should be able to find information on upcoming talks. I see this hasn't been updated here, but we'll get that taken care of. And you can add yourself to the mailing list if you haven't yet and access the recordings of past talks. And as always, if there's any interest in presenting in the future at a future webinar, please fill out the form. We're always looking for people to present here. And I know we currently have spots available over the next few months. So I encourage you to give a presentation and just maybe have some informal discussion about your work. So finally, if you have questions for the speakers during the presentation, go ahead and post them in the discussion document. That's also in the chat box, and I'll probably periodically throw it into the chat box, make sure it doesn't get lost. And so go ahead and use that for questions. And today we have two great presentations. Marlos Goes going to speak about the impact of the western boundary currents on extreme precipitation. And then after that, Dongmin Kim is going to speak about their work on the Quad States tornado outbreak in December of 2021. So we will go ahead and get started. I'm going to turn it over to Marlos. And Marlos, I'm going to make you presenter now. There we go.
Okay, all right.
Yeah, Marlos, you're going to have to change those display settings again there.
All right.
Yep. Perfect.
Good. Thank you. Thank you, everybody, for coming. Thank you, Mark, for the introduction. Today, my talk is kind of a progress report of the work we've been doing in the past year, couple of years. And so I'm going to talk about the impact of the western boundary currents on extreme precipitation. This talk will be divided in two parts. One is a study from along transect measurements, new measurements that we've been deploying. And the second part will be on the high resolution model simulations. So I want to acknowledge my team members. This is mostly the work of Rebecca Fudi. She was a La Penta intern, student intern, Noah La Penta student in the past summer. And she's been working on these meteorological measurements. And also we had the pleasure of having Somi Chakraborty. She was a postdoc with a year with us, and then she moved to the Imperial College in London. And also I want to thank Shem Pudong. She's a OPI from AOML, from Norway AOML. And I greatly appreciate our collaborators. We have a close contact with our collaborators, Leo Siqueira, Emily Becker, and Ben Kurtman from UM, and Greg Foltz and Gustavo Goni from AOML, and Mauro Cirano from the Federal University of Rio de Janeiro in Brazil. Just a brief outline. As I said, the talk will be divided in two parts. So the first part is related to the expandable bathythermograph or XBT project, in which we started deploying a meteorological station. As you see a picture there, along these fixed transects. And this is the first analysis of this new data. We'll compare with the reanalysis, then SAP2 and the ERA5, and SAP2 in the 3-hourly data, ERA5 with the hourly data. And we calculate the turbulent flux and compare the turbulent flux with this reanalysis. And the second part, we'll focus on the extreme precipitation in Southeast Brazil. So we will analyze the impact of the ocean model resolution and this precipitation, and talk about potential mechanisms. And at the end, I show the ANOVA. So first, I'll introduce the XBT network project. So XBTs are single-use probes that we deploy from volunteer ships, generally merchant ships. We deploy 1 to 3 measurements per hour, about 25 kilometers in a high density along these fixed lines, and for decades now. And it measure water temperature in the top 850 meters of the water. And this study will focus on the AX4 and AX7, the top 2 maps there, which are across the North Atlantic from east to west. And also, I'm going to talk briefly about the new measurements we're going to deploy at the AX97 in the South Atlantic. So on those XBT volunteer ships, we started deploying since 2020, these shipboard meteorological stations. And yeah, so this is in the North Atlantic. In the South Atlantic, we already delivered that, but due to operational constraints and during COVID and everything, we had to delay the first deployment. But we are in conversation with the Brazilian Navy, which will carry out these measurements. So it measures this flux every minute, these parameters, and the parameters we measure there is surface air temperature, sea level pressure, and relative humidity. And you see by the picture that the station is about 40 to 50 meters above the sea level. These are big cargo ships, big container ships, so it's high in the ship there. And just to say, the overarching goal here is to analyze the SC processes in extreme heat, to relate to extreme heat and rainfall events, with emphasis in the western boundary current location, right? So here in the maps, you see how important, like, this is precipitation variability and how tight they are to these western boundary currents and their extensions. And we see also how a few of these XBT transects, they can cross these boundary currents in the north and the south of the Atlantic. And the current tasks we have on this now is to do the quality control of the data, because this is the first time we analyze it, and we do the turbulent flux calculation, and we then compare with this satellite and reanalysis measurements products, right? And the future plan, as I said, introduce that to the South Atlantic, and new measurements as we manage to improve the instrumentation. So the first, for this data, right, to see here the section where we measure surface air temperature. And first, we need to do a quality control. So we have issues with the GPS error, spikes, or data repetition, or data overland, and physical values, right? So we do this quality control of the data that we developed, and we interpolate this to the XBT station, to the XBT profiles, because this is where we get to the sea surface temperature from XBTs. And we adjust the height, as I said, the station is about 40 to 50 meter height, and we want to bring that to the regular time, to the standard of these measurements. So to do that, we calibrate on the sea level pressure from ERA5. And first, we see on the bottom left, we see that there's an offset between the sea level pressure and the observations. So for each transect, we get this mean bias, which is about 5 to 6 millibars, and correct that. And you see that the correction on the right, after the correction, we have a pretty good relationship. And then after that, we put on the standards and also correct the surface air temperature and relative humidity from using the equations of the atmosphere. And then of course, we define the sea surface temperature from XPTs, and we find that 5 meters was the best correlation we have with the sea surface temperature from satellite. So we define that as the standard for the sea surface temperature. Yeah, when we compare these observed variables with the ERA5 outputs, we see that pretty good relationship between SST, air temperature, sea level pressure, and relative humidity. So relative humidity will have more variability than the others, but in general, we have a pretty high coefficients of over 0.9 between the measurements and the reanalysis. Just the relative humidity is a little lower, 0.78. So for the NSAP variables, we see that we also get good relationship between sea level pressure and surface air temperature. But you see on the top right, you see that there's a cold bias we find on the NSAP, about 0.3 Celsius. And also the relative humidity, you get a big drop in the correlation all the way to 0.44, which you find in the NSAP data. And then from this, we calculate the turbulent heat fluxes, which is our goal here. And we calculate the latent heat and the sensible heat using the core 3.6 equations. And since we don't have all the observations to calculate these turbulent fluxes, we use part from the reanalysis. Since ERA5 had the best correlation, we use ERA5 to be able to calculate this. And then we compare with the fluxes calculated from ERA5 and NSAP2 variables that we calculate in the same way. And we see here that in agreement with the previous results, that ERA5 had a better correlation of 0.89 for latent heat and 0.91 for sensible heat. And NSAP has a little bit lower and a little bit of offset, especially for the sensible heat flux. Yeah, when you go to look at just one transect across the Atlantic, we can see on the left side how the observed and the ERA5, they match pretty well across the Atlantic, and the NSAP has this bias on the sensible heat flux. And by looking at the components of the heat fluxes that we calculate for the latent heat, we compare with the relative humidity for ERA5 on the top and NSAP2 on the bottom, and for sensible heat against the air temperature. And we see that the high correlation of these variables with the heat fluxes as we expect. So we see that the biases, for example, the bias that the air temperature bias is what's driving the sensible heat biases as well. So just a bit conclusion. So this is a work in progress, and Rebecca is with us finalizing all the analysis. And we see that relative humidity tends to disagree across the three scenarios, and is the one that disagree the most again relative to the other variables we analyze. The surface temperature shows general cold bias of 0.3, especially in the NSAP. And the observed variance and the fluxes tend to agree more with the ERA5 than with the NSAP2, at least in this analysis that we did. And so as we said at the end, the latent heat fluxes are generally more dependent on relative humidity and the sensible heat on the surface air temperature, as we difference between the reanalysis as we saw it. In the second part, I want to focus on the summer monsoon in South America. So this is a monsoon system. For example, 50% of the rainfall in the tropical and subtropical South America happened during just December to February. And for example, here, just a month ago, in February 2023, some locations, especially near the coast in the state of São Paulo, suffered nearly 700 millimeters of rain just 24 hours, causing flash floods and landslides. And some people had to be evacuated before this rain. So it's very important to have a good forecast, not only the time and the intensity as well of these events. So one particular feature of the this monsoon system is the South Atlantic convergence zone. So the South Atlantic convergence zone is also responsible for probably like 60% of this summer rain there. And so it's linked to the teleconnections from the Pacific towards the Atlantic, especially in these intraseasonal timescales where we have MJO and other teleconnections. But also you have a local effect as well. And one of the local effects, in a recent paper by Pezero 2022, they talk about this thermodynamic feedback and the dynamic feedback. And the thermodynamic feedback, which would be, you see from the picture on the bottom left, you have this cloud cover, and then you have this reduction of the shortwave radiation to this cloud cover, cooling the sea surface temperature. And the other is the dynamic feedback, with the ocean has its part as well in terms of upwelling, horizontal advection, and eddies. And you see the picture on the right, on the bottom, you see that you see also the events, the precipitation band over the continent and going all the way to the ocean. But the cooling is not only restricted to under this precipitation, but also south of it. And then there's seems that the ocean dynamics and eddies are responsible for that. So that would impact the variability of this precipitation band. So the objective here is to understand the role of the mesoscale on the airscape feedback to the extreme precipitation events in South America. So these events, as you see the figure on the side, it has this kind of dipole pattern, and it depends on the pattern of the wind, and then it will have this band going all the way from the Amazon all the way to South America and the ocean part. And the methodology here, we use retrospective forecasts. So these are forecasts that start in 1st of January of each year from 1982 to 2015. We analyzed 3 ensembles in 3 ensemble members for 2 ensembles. One ensemble, we have a low ocean resolution, where we call LR, which is eddy parametrized ocean, more or less 1 by 1 degree, which is about the same resolution of the atmosphere in both experiments. And one, the high ocean resolution, the HR, which is eddy resolving ocean of 0.1 degree resolution. And for this analysis, we just focus on the summer, which is January to March, and interseasonal variability, so more or less 0 to 3 months, we do a high pass filter on this on all the variables, and we analyze most composites of the 90th percentile of precipitation. Here we show the 3 regions, and we focus mostly on the Sabra region. That is the one that is really caused most damages in the area there. So the Sabra will be most of the composites related to that. and talk a little about the model. So why you think the model should have an effect there, right? So we compare here the standard deviation of the sea surface temperature against observations, and we see in the observation this region in the West and South Atlantic of high SST variability, and you see that the high resolution can reproduce well this variability as well as the amplitude of the spectrum there. And this is mostly due to eddies and meandering and fronts in the region. Actually, the high resolution can even have a little bit more variability than observation, which we don't know if it's because of observation of the model itself. But in the LR, this variability is suppressed, and the amplitude of the variability of the spectrum is much lower too. And then if you look at the precipitation variability, what we want to focus on, and compare to the observations for January, February, March, and we see that generally the models, they underestimate a little bit the variability of precipitation, but the high resolution model can show more variance than the low resolution. And this is just because of the ocean model resolution. So talking more in general about the convergence zone event, South Atlantic convergence zone. This is also for the SEBRA region. Here we compare the 90th percentile against the 10th percentile, and this is the precipitation and the surface wind pattern. And you see that when you have this band of precipitation for the north, we have the wind, this cyclonic circulation of the wind, bringing all the moisture and the rain further north. Whereas when you have the opposite, we have a dry anomaly, the winds rotate to the other side. So this is how the high resolution model, from the high resolution model, which is in agreement with observations from previous studies. And looking more a comparison of these extreme events. So I have observations, the high resolution, the low resolution. Again, for the precipitation there. And when you look the bottom panels, the difference between high resolution observation, low resolution observations, and the two model, the difference of the two model. Again, we see that the models tend to show a little less precipitation than observations, but we have the high resolution compared to low resolution. It can capture more extreme amplitude of this precipitation variability. And you look on the panel on the right, and you see this is how this convergence zone events, this is how it evolves over time from a lag to -5 to +5. And you see that these events, it tends to, that they have a duration of more or less 8 to 10 days. And you see that the high resolution, the red ensemble, or the T ensemble members, they are much more compared to observations than the low resolution. And in addition, this is about a 30% increase. And in addition, they capture this dual band of precipitation that we see, one over land and one over the ocean, that the low resolution can't capture. And if we look at the SST variability during the event from a lag to -20 day until 20 days after the peak of the event, we see that both observations and high resolution, they have a high SST before the event, and up to -10 days and even a little bit longer. And then you have, and the low resolution doesn't show that feature. At the peak of the event at lag 0, we see that the observation high resolution, they have a cooling, a much stronger cooling that extends much further south than the low resolution. And this is, again, what people said about this dynamic feedback. And then at the same time, it stays much longer too, much longer over time at lag +10 and plus 20, these cooler anomalies stay for much longer. And so it has a better comparison with the observations. And we see like the main features during the peak of the event. These are just the composites for the high resolution on the left and low resolution on the right. And again, we see on the top of the SST, you see a much stronger and more prominent cooling in the high resolution, not only extend below the rain band, but further down. And we have the cyclonic winds in both simulations here in the second panel here, and which is related to the large scale process that we talked. So both models can capture this large scale process, but of course the high resolution can capture a little bit stronger, at least from the composites we have. And what is the biggest feature here is the mixed layer depth anomaly. So the mixed layer depth in the high resolution go much further down, up to 5 meters increase, and that's what keeps that cold water for longer during the event, whereas in the low resolution model, the mixed layer variability is very little. So this is where the dynamics come from. And then at the bottom panel, we look at the radiative cooling and turbulent cooling. The radiative is the magenta line, and the turbulent is the red and the black line. So they kind of show similar pattern, right? We have the cooling, radiative cooler under the high precipitation, and the turbulent further south. And we have this Ekman in shading the Ekman pumping. So the Ekman pumping is almost stronger here. It's also stronger in the high resolution simulation, what helps the cooling in the region. So we are analyzing, so this is a work in progress. We are now working on trying to understand the mixed layer heat budget there for the low resolution and the high resolution. But you see that the features in the high resolution are really stand out in terms of the temperature tendance. Heat fluxes, they kind of similar, and the vertical advection because of the Ekman pumping is also stronger in the high resolution. So just to conclude, we have both models capture the large scale feature of atmospheric circulation. The eddy resolving model improves the interaction and improves the extreme precipitation up to 30%. And this is because of the high variability of SST and mixed layer depth, and also the heat flux variability. And yeah, I think my time is here. So we just give a last message that this results may suggest that the eddies can improve the subseasonal to seasonal prediction of extreme precipitation. And here I want to add the acknowledgement. So thank you for your time, and I'll pass it to Mike.
Okay, thank you. We have, actually it's not a question in the document. I'm getting some feedback, I think, from your mic and speaker there, Marlos. I'm going to go and mute you for a second, see if that helps. Okay. There is a comment in the document there about the 12th session of the ship observations team will be in Melbourne, Australia, May 15th or 18th. Be in hybrid format. I said prior to that session, there'll be an XBT workshop hosted by the Ship of Opportunity panel on May 11th and 12th. And there's a website listed there as well for more information about the workshop and the meeting. So let's see. There's one quick question maybe we have time for. Marlos, it's being typed in right now. Does the vertical divergence of turbulent heat flux beneath the surface play a role in controlling the vertical velocity and thus the SST cooling during the event? And let me unmute you here.
So could you repeat the voice is a little low on my computer?
Yes. Does the vertical divergence of turbulent heat flux beneath the surface play a role in controlling the vertical velocity and thus the SST cooling during the event?
Oh, yeah, I am not. So we are working on the heat budget right now. So the thing is that the problem we have here in these simulations is that we just have surface properties. So for example, to estimate we have mixed layer depth, and we have sea surface temperature, and we have the fluxes. And for example, for the vertical advection, I had to do some estimates of what would be the vertical advection from maximum pumping and mixed layer depth tendency. And we don't have a subsurface temperature, so we kind of an estimate from other RNAs, so RS5 and etc. So we have an estimate of the subsurface temperature, but yeah, this is an interesting thing, but it's hard to have in these high resolution models, right? The daily subsurface temperature is just too much to store, but that is a good question.
Okay, thank you. We need to move on to the next presentation. Dongmin, I'm going to make you presenter here, and I will let you take it away whenever you are ready.
Can you see my screen?
Yes. Yep. Looks good.
Okay. Let's start. Hi, I'm Dongmin Kim at University of Miami CIMAS and NOAA AUMA. Thank you for giving me a chance to present my work here. So today I will talk about the quad state tornado outbreak, which occurred in December 2021. The main objective of this study is to find out what physical mechanism drive to generate this quad state tornado outbreak. And this bar graph shows fatalities by extreme weather events. According to the US Natural Hazard Statistic Report, tornado is one of the hazardous weather events. So, as similar to this other extreme event, the tornado activity has large seasonality. And this is the climatological tornado number in the US. The tornado increased sharply in early boreal spring and then decreased rapidly after boreal summer. And this is the special pattern of the tornado genesis during the May to July. This figure is from the my recent paper. The most active area is the central US, including Texas and Louisiana, as we call the tornado alley. However, the occurrence of the significant tornado outbreak is not only limited to the boreal warm season, but also to the cold season. And this is the same as the upper figure for the cold season. So please note that the color bar is smaller than this in the warm season. And main feature of the cold season tornado is the eastward shift of the active tornado area. So, but the cold state tornado outbreak was not included in this center of the cold season tornado active area. So this figure is the tornado report from the NOAA SPC during the cold state tornado outbreak. And EF3 and EF4 tornado were traveling from the Arkansas to Kentucky. And this is a very unusual case. And also, this is the longest traveling cold season tornadoes in the historical period. As I mentioned in the previous slide, compared to this cold season climatology of tornado activity, the main developed area of this cold state tornado outbreak is shifted northeastward. There before, the cold state tornado outbreak unexpectedly infected on the large populated area. So during this event, we had 89 fatality and 672 injury and 3.9 billion estimate damage. So many lives and property were lost during just only 2 days. So this terrible event suggests that we need more study for the cold season tornado activity. So trying to get a hint of what caused the cold state tornado outbreak, we first look at the large scale condition during the cold state tornado outbreak. So this is the 500 hectopascal geopotential height as a black contour and SST anomaly as a shading during the cold state tornado outbreak. So we can find the 3 clear large scale conditions during this event. A negative PNA-like pattern and 1 Gulf of Mexico SST and La Nina. So interestingly, the strong negative PNA persisted for more than 10 days prior to the cold state tornado outbreak. And in this figure, the shading is to meet the temperature and vectors are particularly integrated moist flux. And this shading indicates the low-level wind shear and purple contours are lifted index. So, and black dots are tornado genesis during the cold state outbreak. So due to these large-scale conditions, the low-level wind shear and humidity temperature increased the eastern U.S. And moreover, the lifted index over the eastern U.S. is a strong negative value, which means an increase in the atmospheric instability. And also, the particularly integrated moisture flux increased over the eastern U.S. So these all conditions indicate the favorable condition for the tornado genesis over the eastern U.S. But actually, the previous study have already suggested the link between the 3 large-scale condition and U.S. tornado activity. For example, the Wang et al. 2021 showed that the first model of the singular value decomposition of tornado activity is closely linked to the negative PNA-like pattern. As you can see that this pattern is very similar to the cold state tornado outbreak. And next one is the 1 Gulf of Mexico, SST. Additionally, in this figure, Molina et al. 2018 found that the 1 Gulf of Mexico SST enhanced the probability of a significant tornado environment during the boreal winter, while the cold Gulf of Mexico SST reduced the probability of tornado environment due to the change in moisture supply from the Gulf of Mexico. And last largest scale condition is La Nina. So, Allen et al. 2015 addressed that La Nina increased the tornado and hail occurrence during the boreal winter, while El Nino decreased due to the meridional shifting jet stream. So many previous studies suggest that each independent large-scale condition can affect tornado activity. However, there are few studies to investigate the connection between these large-scale conditions, and it is still unclear what large-scale climate variability is the major factor for generating cold season tornado outbreak, such as a cold state tornado event. Therefore, in this study, we investigate the cause of the cold state tornado outbreak and a physical link between these large-scale environment and cold season US tornado activity using observation and model data. In this study, we used the daily OISS data and NC1 Liansis data for investigating a large-scale condition. And tornado data is from the NOAA SPC report data. And we only counted tornadoes that are equal to or greater than one of the Fujita and Ines Fujita scale. And study period is from the 1918 to 2021. And we only focus on the cold season, November to January. And all data are remove the linear trend to avoid the influence of the global climate change. And we also use the daily linear 3.4 and Gulf of Mexico index, which are specially averaged in these boxes to define the warm and cold phase of each index. And daily PNA data is derived from the PSA. And positive and negative phase of each index are defined by over and less than 0.5 standard deviation of each index. And to verify the result from the observation and the analysis data set, we use the 400 model years in CSM range with pre-industrial CO2 level. And so to explore the impact of 3 large-scale environment on the cold season US tornado activity, we use the convergent analysis. First, we explore the impact of the negative PNA on the tornado genesis and associate environmental condition. So you can find that negative PNA is associated with strong anomalous high and low over the northern Pacific and Gulf of Alaska. And it also produces anomalous high along the eastern US seaboard. And this positive geopotential height anomaly enhanced the Northern America low-level jet and moisture flux from the low-level and low-level wind shear over the southern and eastern US. And it also produced the above average temperature across the southern and eastern US and positive oil anomaly along the eastern US seaboard, which in turn increased the surface temperature. So these atmospheric conditions increase the atmospheric instability over the southern and eastern US, which in turn increase the tornado genesis over the southeastern and eastern US. Next, we examine the impact of the warm Gulf of Mexico. The consistent with negative PNA case during the warm Gulf of Mexico case, there are failed anomalous high and low over the northern Pacific and Gulf of Alaska, even though it is weaker than negative PNA. And there is also anomalous high along the eastern US. So the spatial pattern of the 2-meter temperature and outgoing long-wave radiation and other environments are highly consistent with those during the negative PNA. So therefore, the tornado activity also increased over the southeastern and eastern US during the warm Gulf of Mexico. However, during the La Nina, there is no clear negative PNA-like pattern. The anomalous atmospheric high centered in the northern Pacific stretched out to the southern US, and so there is no clear atmospheric high over the eastern US that produced the anticyclone circulation over the eastern US. But consistent with the previous study, during the La Nina, the cold season US tornado activity increased. However, it is weaker compared to that during the negative PNA and warm Gulf of Mexico case. And also, spatial pattern of the environmental condition are quite different from those during the negative PNA and warm Gulf of Mexico case. So this result clearly shows that the La Nina condition is not a necessary component to generate a negative PNA-like pattern, which is a major contributor to an increase in the cold season US tornado outbreak, such as the cold state tornado outbreak. So we confirm the observational result using the CSM range 400-year simulation. So as shown in this figure, the spatial pattern of the SST and geopotential height at 500 hectopascal in CSM range are highly consistent with the result from the observation and analysis dataset. So as you can see that the spatial pattern of the geopotential height during the negative PNA is very similar to the to this during the warm Gulf of Mexico case. So, and this pattern is very is consistent with the cold state tornado outbreak. So this result may suppose that the negative PNA is linked to the warm Gulf of Mexico and cold state tornado outbreak. So next step is to explore the physical link between the negative PNA and warm Gulf of Mexico SST. To examine the relationship between the PNA and Gulf of Mexico SST, first we calculate the histogram of the Gulf of Mexico SST during the negative and positive and neutral PNA phase. Even though the histogram are skewed, during the negative PNA, the occurrence of the positive Gulf, occurrence of the warm Gulf of Mexico SST is more frequent than that during the neutral and positive PNA phase. In contrast, during the positive PNA, the cold Gulf of Mexico SST is more frequent than this during the negative PNA case. So we also calculate the lead lag correlation between the PNA and Gulf of Mexico SST. So this lead lag correlation shows that a negative PNA phase lead the warm Gulf of Mexico SST with a lag of 6 days. And this result suggests that when a negative PNA persists for longer than 6 days, warming Gulf of Mexico SST are maximized, while when a negative PNA persists for less than 6 days, the Gulf of Mexico SST not significantly warm. And this result is derived from the CSM range. So all results from the CSM range are highly supporting the observational result, even though this lead time is a little bit longer than the observation. So based on the our finding, we set up the hypothesis of the cause of the cold state tornado outbreak. The hypothesis is that a persistent negative PNA can generate a blocking high over the eastern U.S., which in turn leads to the northward shifted jet and clear sky to heat up the Gulf of Mexico. And additionally, the persistent negative PNA and associated atmospheric leak centered over the eastern U.S. enhance the moisture flux from the Gulf of Mexico to the eastern U.S. and increase the atmospheric instability over the eastern U.S., which are favorable conditions for generating tornado across the Mississippi Valley and Ohio Valley, where the cold state tornado outbreak occurred. So to examine this hypothesis, we separate the two negative PNA cases. One is the short-lived negative case, which is persisting the negative PNA for less than 6 days. And second one is the long-lived PNA case, which is the persisting the negative PNA for equal to or more than 6 days. So for example, from this figure, this case is short-lived negative PNA case, and this case is the long-lived negative PNA case. So the cold state tornado outbreak is one of the longest long-lived negative PNA case. So first we first look at the short-lived negative PNA case. During the short-lived negative PNA case, there are common structure of the negative PNA like geopotential height pattern. For example, paired anomalous high and low appear over the Northern Pacific and Gulf of Alaska. However, the atmospheric anomalous high over the eastern U.S. extend meridionally. So this meridionally extended atmospheric high produced the low-level southerly wind anomaly and increased moisture flux over the central U.S. So this in turn increased the atmospheric instability, such as low-level wind shear and lifted index and humidity temperature over the central U.S. Therefore, the tornado genesis is likely to occur in the central US. But on the other hand, during the long-lived negative PNA, where the atmospheric high and low over the northern Pacific and Gulf of Alaska is consistent with the short-lived negative PNA. However, this anomalous ridge lies along the eastern US seaboard, which is similar to the cold state tornado outbreak. And this anomalous high lead to an increase in the low-level southwesterly wind anomaly over the central and eastern US, thus increasing the atmospheric environment instability and extending the North American low-level jet toward the central US. And additionally, the anomalous high along the eastern US seaboard produced a strong positive weather anomaly over the Gulf of Mexico and eastern US seaboard, which in turn increased the Gulf of Mexico SST. So this condition extend the strong atmospheric instability northeastward. So as a result of this, the tornado genesis shift northeastward during the long-lived negative PNA compared to that during the short-lived negative PNA case. So I just overlapped the tornado genesis during the cold state tornado outbreak onto the long-lived negative PNA case. So you can find that this pattern is highly consistent with each other. To confirm the observation data set, observation data, we did same analysis using the CSM lens. So the result in the spatial pattern of the SST and geopotential height at 500 hectopascal in the CSM lens strongly support our hypothesis and a result from the observation. For example, this during the short-lived negative PNA, there is no clear warm Gulf of Mexico SST, and there is extended atmosphere reach meridionally. On the other hand, the long-lived negative PNA shows warm Gulf of Mexico SST and a similar geopotential height pattern to the cold state tornado outbreak. So these results suggest that a persistent negative PNA and associated warm Gulf of Mexico SST are crucial key for generating the cold state tornado outbreak. So I will summarize today my talk. We explore the physical link between the climate variability and US cold state tornado outbreak on December 2021. So as shown in this figure, the long-lived negative PNA produced this atmospheric high along the eastern US seaboard, producing the warm Gulf of SST and the southwesterly wind anomaly, which in turn increased the moisture flux and atmospheric instability over the Ohio Valley, where the cold state tornado outbreak occurred. But on the other hand, during the short-lived negative PNA, this led to the increase. This anomalous high meridionally extended over the eastern US. So this led to the increased southerly low-level jet and moisture flux from the Gulf of Mexico into the central US. So this in turn increased the atmospheric instability over the central US. So therefore, the increase in the tornado genesis is shifted toward the central US compared to the long-lived negative PNA. This is all I have. So thank you for your attention.
Great, thank you very much. Do we have any questions in the document? I don't see any. Does anybody have any questions for Dongmin here? If so, if you can unmute, feel free to. Otherwise, you can type them in the document. Let's see, question coming in now here. So the question is, do the southwesterly winds associated with the longer-lived PNAs cause any reduction in wind shear? And then, the knowing tornadoes typically thrive on low-level wind shear. Yep. So, are you able to answer that?
But the addition in this figure, the tornado the low level wind shear during the long-lived native PNA is much stronger during this eastern U.S. area. So maybe it is not much effect to reduce the wind shear, low level wind shear at this area. But I'll check it.
Okay. One more question coming in here. I'll wait for Christiana to finish typing here. Okay, Christiana Stan asks, how robust is the short-lived PNA? The time series shows the negative values, however, the pattern of Z500 does not show a typical PNA pattern.
Actually, when we collect the short-lived negative PNA, we only counted when the PNA value is over this 0.5 standard deviation. So maybe it is. I think it is. I believe that this is the robust, the negative robust. And the pattern is over this Pacific and Gulf of Alaska shows the typical PNA-like pattern in this area, but this secondary atmospheric ridge is a little bit different, which is the extended meridional. So this one, this one is the CSM range result. So maybe it could be different from to the observation. But this meridionally extended secondary atmospheric ridge is also shown in the CSM map. And this is also, I just only counted the negative PNA phase is less than 0.5 standard deviation in the model.
Okay, great. Thank you very much. Anyway, if anybody else has any other questions, we are at the top of the hour right now, but please go ahead and type them into the discussion document. I'll make sure that the presenters actually see them and they can come in and answer them, and you can check back for that. So Anyway, I want to especially thank the both speakers today for presenting these great talks, and I will hope to see you all next month. So keep an eye out for the announcement of next month's speakers. So thank you very much, and see you all next month.
Bye bye. Thank you.